ELead, robots for efficiency. Here at ELead, we live by the need to provide a fast, accurate, and efficient way to fulfill online orders. We strive to fulfill the needs of each company who partners with us and adapt to each partner's standards.
ELead's packing robot was built to fit OSHA regulations. The footprint of the robot's base fits 36 inches squared of space, and the whole robot fits and can operate in a 3 by 3 by 3 foot volume. While filling orders, efficiency is increased by the accuracy of our robot, which fills orders with exactly what needs to go in 95% of the time.
Now, we suppose you all are wondering how we got here. Let's take a look at our design journey, starting from sketches all the way to our final CAD designs. When we originally went to look at making a packing robot, we created 3 sketches. Our first concept sketch used the idea of a jointed robot arm with a basic box-shaped base. It also focused on the design of our gripper. Secondly, we looked into using dashpots to move the robot up and down. It drew inspiration from adjustable chairs. Our last concept sketch created a new idea for a base, in which the surface area of the robot touching the ground became separated in 4 different sections.
From these design sketches, we worked on proof of concept prototypes. This allowed us to better judge what would be possible for the robot. We designed 3 proof of concept prototypes, one for each section of the robot. We started with a model of the robot arm, running with the idea of using dashpots to create movement. Using plastic cups and straws, we were able to see how the dashpot would push up the top layers upward. We also wanted to model a basic format of the base to see what kind of support would be needed to hold up the rest of the robot. Using paper plates, skewers, and straws, we were able to build a general form of a base. Lastly, we made a prototype of our gripper. This allowed us to see how the gripper paddles would slide back and forth to collect and let go of the order boxes.
Our next step was to combine our sketches and proof of concept models and move into CAD. We went through many base designs. Various ideas included a base with a single footprint, while others had multiple feet. Another key feature we modeled in every base model was a place to add weight in order to make sure the robot would not tip over during operation. We also drafted the gripper in CAD. This really helped us see where the joints would have to be located and how much surface area would be touching the boxes at a given time. When it was time to make final decisions on what we would use for the final robot design, we included our background research and all restrictions to make sure we had the optimal design. During the process, we consulted with Troson Robotics to gain inspiration for grippers. From this, we could see various ways boxes can be picked up. The gripper was designed to pick up all order boxes, being able to extend just enough to fit itself around the boxes securely. For the base, we picked a design that fit within OSHA's allotted surface area of robot to floor, yet making sure it would be sturdy enough to support the robot and the boxes it will pick up. As well, we made sure that there would be enough area for the order boxes to be placed within the OSHA-regulated volume for robot operations. Our arm is based in simplicity. In order to create less interference between joints and ease of operation, each joint is placed on a section of the robot that is unique to that joint. Let's take a closer look at these parts. For our gripper, we used a system in which one of the paddles can slide back and forth in order to grip and release the order boxes. Additionally, one joint was placed where the pin that holds the gripper connects to the main arm of the robot. This is the joint that moves up and down, allowing for the gripper to be lowered and raised.
The extending mechanism allows for the packing robot to reach the furthest spot in the 3 by 3 by 3 foot volume space. The arm would be attached to both the gripper arm and the rotating arm. The rotational mechanism allows for the robot to rotate in a full 360 degrees, both clockwise and counterclockwise. The mechanism now completes the robot as it is able to move its claw freely around and is ready to tackle lifting boxes and ship them to the customer.
In this animation, you can see how the robot will move in order to pick up boxes. To assure you the ability of our robot, we prepared some physics information. For our gripper, we have calculated the pressure that the grip will have to apply to the heaviest order box to pick it up. Assumptions were made that the exact area of the gripper paddle applying the pressure to the box is 0.29 meters squared. The heaviest box reaches 1.36 kilograms, and the maximum height the box must reach is 0.46 meters. In order to calculate force, we multiplied the mass of the heaviest box by gravity to calculate a force of 13.34 newtons. Then, to calculate pressure, force is divided by the area of the gripper, which had us find that it will take 46 pascals of pressure to grip the box. We also wanted to add how much work will be done by the robot. We used force times height the box must reach to find that the work done will be 6.14 joules.
Now for the physics that regard the rotation motion the robot is going to be undergoing. We calculated that a motor with a max torque of 180 Newton meters and the radius of the arm doing the rotation is 5.7 centimeters in the radius. The maximum force able to be exerted is 80 newtons. Then, while trying to find acceleration, force and mass were already given, leaving acceleration to be solved. The average acceleration using these numbers is 26.40 meters per second. The motors were chosen this powerful as they are lifting boxes and will affect the way the robot moves. Similarly, with extending and gripper arm, the same 180 Newton meter motor is going to be used and are both capable of traveling at 0.81 meters in 5 seconds at a velocity of 0.162 meters per second.
In order to show that the robot will not tip over during operation, we use the equation showing that the section with the gripper and the heaviest box must be lighter in weight than the section with the base. Using weights of materials given to us by our material supplier, we were able to create ratios to find the exact weight of each smaller component of the section. This group of components came in at 3.78 kilograms, meaning that the other section of the robot would have to be heavier than this. Again, using our data from our material supplier, we calculated weights of each component. This section totaled in at 15.58 kilograms, heavier than the other side by almost 12 kilograms and supporting the movement of the robot. So now that you know our product from front to back, we want to assure you of our ability to fulfill what you ask of us. Let us show you some behind the scenes of how ELead makes it work. We build our robots for companies with online delivery services who want a more efficient packing process with less damage to orders. Our new robot packing arm will speed up order assemblies and decrease damage by using controlled electronics. From us, you will receive the installation process. The materials the robot is constructed of are simple and help to provide a fast assembly. We have also partnered with a repair company that can come and fix your robot should damage occur. We spend money into research and development, software, and marketing our product. From our sales of our robot and the repair process, we put this back into the company to create better products. ELead is proud of what we have accomplished. We hope that you will be our next big partnership.